we've got resistors in series and resistors in parallel. This is a drawing for resistors in series and the subsequent drawing for resistors in parallel. We already know these equations, it's what we've been using. And we can actually do something very similar for capacitors. Just like we can reduce two resistors to one resistor using this equation, we can reduce two capacitors that are in series with this equation. If we're saying that C is the value of the capacitance, then this would be C1 and this would be C2. The equivalent capacitor value would actually look a lot like the equivalent for parallel that we have for resistors.
That's supposed to be C1 and C1.
C1 and C2?
No, up on the diagram.
Oh, thank you. Yes, that's at C2.
So can there be a C4?
Sure. Saw it coming. And then if we have capacitors in parallel, typically the battery symbol, I know because the battery looks a lot like the capacitor symbol. It's just one side is shorter than the other. Typically you'll see like a 5 volts next to a battery, so that will help you distinguish between the two. So the equivalent capacitance for this parallel, for these parallel capacitors, is going to be C equivalent is equal to C1 plus C2. Right, so it's like resistors except switched. Yep. So here we get a picture of, so all of these things are in series. We got our capacitor equation and our capacitor equation here and our resistor equation here. In parallel, we have our resistor equation and our capacitance equation. So the objective here is to combine all of these resistors into, thank you, all of these capacitors into one capacitor. So finding the equivalent capacitance. So I like to think about it as kind of like I'm unraveling this bent shape. And I guess maybe just I've got more experience with it, so it makes more sense to me. And I think a convenient way to think about this, and of course you should try this on your own before you continue watching the solution, is I like to start at A and then go along. So I'm drawing this A, and I get to that 5 microfarads. And then I get to this junction, and maybe I can do a split. And I'm gonna let's go through the bottom split first, or through the 4. So here's the 4. So there's the 4 microfarad, and then after the 4 microfarad, I come back to a junction. So I'm gonna go ahead and draw that junction. And I'm going to go out of that junction, and I'll get the 6 microfarads. No, it's too loud. It's not fun anymore.
You were the one who wanted me to do it.
Okay, so now I want to complete this upper part. So rather than going down through the 4 microfarad, I'm going to go to the right through the 24 microfarad. So I'm going to go through the 24 microfarad. And I'm going to continue through the microfarad, and I'm going to get to the 12 microfarad. And I'm going to continue through the 12 and get to the 8. And then I'm back at that junction after the 4. So now we can see that the 24, the 12, and the 8 are all in series. The 24, 12, and 8 are then all in parallel with the 4. And then this whole equivalent resistance of that parallel circuit that I just identified is in series with the 5 and the 6. Okay, so now that we've identified that these 3 are in series, those are the ones we're going to want to deal with first. So to find the equivalent resistance for this top one, I can do 1 over Q equivalent, or sorry, C equivalent, 1 over C equivalent is equal to 1 over 24 plus 1 over 12 plus 1 over 8. And that gets me, good. So I get 1/4 here. So that means the equivalent capacitor is going to be 4 microfarads. So I can go, I still have this capacitor, and then now instead of writing 3 capacitors, I can write 1 that's 4 microfarads. And then with everything else unchanged. Okay, so now these are in parallel, so I can combine them. And then the capacitance equivalence when they're in parallel is equal to simply the addition of those. So the equivalent capacitance for these two is 8 microfarads. So then replacing that one, leaving everything else the same. Now these last 3 are in parallel. Sorry, they're in series. So I have the equivalent capacitance being 1 over 5 plus 1 over 8 plus 1 over 6, which comes out to be 120 over 50. Okay, so I get this being 59 over 120. So then the equivalent capacitance is 120 over 59, which is about, it's 2.03 microfarads. So that means I can now write the original circuit with one capacitor and say that it's 2.03 microfarads. So now that I'm recording, we're now going to talk about RC circuits, which have a resistor and a capacitor in them. So really what we want to talk about is how the charge builds up on the capacitor. So we're going to get an equation, and I am unable to show you why this equation is true. This is one that would involve hand-waving math for y'all. The charge currently on the the charge currently on the capacitor is equal to the maximum charge allowed by the equation the V equal, or the VC equals Q, or whatever that one was that I had previously. The one that I had over here. That was, I don't remember where I wrote it down. Somewhere in there. I don't see it. Oh, okay. Well, but the previous way that we found the maximum capacitance is what this Q represents. Times 1 minus E to the power of negative T divided by RC. So basically, well, this is the equation that I was about to write down, but then stopped. So now, there it is. So basically, this equation tells us that a capacitor, remember that a capacitor is like two parallel plates that have positive charge on one plate and negative charge on the other plate. Well, what this equation tells us is that the charge that's built up on these plates doesn't build up instantaneously. It takes a certain amount of time. And that time is related to the resistance of the wire and the capacitance of the capacitor. So what we're assuming here is that in this circuit here, DJ, in this circuit here, we have a switch on one end. This is typically how we write a switch that can be closed and open. So when the switch is open, there's no current flowing through because the wires haven't been connected. So there's no complete circuit. But when it closes, then current will start flowing through, and it will start building up a charge on the capacitor. And that charge is going to be determined by this equation here. So we can actually assume with an infinite amount of time that the charge on the capacitor will equal the maximum charge that it can hold. And it turns out that we really only have to wait a couple of seconds. It doesn't really take that long for a capacitor to, well, I guess depending on how large the capacitor is, but so we can get a function that's actually going to look like, so if this is time on the bottom and this is Q on our Y values, this equation is going to look like this, where this asymptote that it's approaching is Q naught, or the maximum charge that it can hold, so Q max. So we can also get an equation about if we were to, once we've charged the capacitor, so we closed the circuit for a little while, we've let the capacitor charge, and then we open it so that there's no connection, then the capacitor is going to discharge itself. It's just going to keep putting out electricity, or current rather. It's just going to keep going, and that, like the electrical energy, like it's not going to go back to the battery, so through the wire it'll just turn into heat. Although it will heat, so the temperature will increase so little that you won't be able to tell that the temperature is increasing. And the rate at which it, or the equation for its energy dissipation is Q. So this is when this is just after switch is closed. Oops, I was about to write switch twice. And this is the equation for the charge on the capacitor just after the switch is opened. And that's going to be Q equals Q max times E to the negative T over RC. So the functions are very similar, you just end up with you don't have this 1 minus in the end. And the graph for this is going to look like this, where this point is basically the maximum, Q naught or Q max, however you like to call it. You can.